Okay, welcome to our concept video for section 3.1, where we're going to talk about exponential functions. So now we're moving on to a new chapter that's all about exponential functions and logarithmic functions, which we'll talk about in the next section. And this is good because now we get to expand the type of functions that we can work with. Up to this point, in chapter 1 and chapter 2, we were really just focused on power functions. All the functions that we worked with were some sort of variation of a power function. If you think about some of the common functions we work with, a polynomial is just a bunch of power functions put together with addition and subtraction with some coefficients in front. Linear functions are just polynomials. Root functions, remember root functions are just power functions with fraction exponents. So now we get to work with a fundamentally different type of function called exponential functions. Why is it fundamentally different? Well, it's really just because we're going to switch where the constant is and where the variable is. So a power function has the variable as the base and has a constant as the exponent. Well, an exponential function switches that, where the base is now a constant and the exponent is now variable. Sometimes you'll see a value being multiplied on the outside of this exponential function. Just like power functions had, sometimes you'll have coefficients. And all those coefficients do is just affect what your starting value is. So hopefully we can see the difference between these two things because they are not the same type of functions. And we're going to see that as we get into derivatives. They have different derivative rules because they're very different functions. They look similar, but they're fundamentally different because of where the variable is. With an exponential function, the variable is in the exponent, and with a power function, the variable is the base. So, what's so special about exponential functions? Well, exponential functions are really useful because they represent repeated multiplication. If you have some number raised to a variable exponent, that means you're multiplying by that number over and over again for an unknown amount of time. We're going to see a lot of applied scenarios where we can use exponential functions for this reason, and we'll look at those in section 3.3 and 3.4. But because exponential functions represent repeated multiplication, there are some ground rules with exponential functions. First of all, we need the base to be greater than 0. Otherwise, what happens when you multiply a negative number by itself over and over again? The number switches between negative and positive. And so to prevent that type of complication, we're just going to assume that my base is always going to be positive. And notice we don't want the base to be 0 because then you're just multiplying by 0 over and over again, which creates a trivial equation because your result is always 0. But for that same reason, we're also going to assume that the base will never equal 1. Because what happens when you multiply by 1 over and over again? The number just stays the same, and once again you have a trivial equation. So, with exponential functions, that base is always positive, but it's either in between 0 and 1, or it's greater than 1. And what's cool is depending on what that base is, it creates two very different types of functions, known as growth functions and decay functions. So, an exponential growth function represents a function that as you multiply the number by itself over and over again, the value is growing. Well, in order for that to be true, your base has to be greater than 1. Right? If I multiply a number by 2, the value is going to get bigger. If I multiply it by anything greater than 1, that value is going to get bigger, which gives me a growth function. If I were to graph a growth function, I end up getting something like this, where it's always growing, but as my x value gets bigger, it starts growing faster and faster. Well, decay function looks very similar, except it's going the other direction. Because with the decay function, as you multiply it by your base over and over again, the number's getting smaller, and the only way that happens is if your base is between 0 and 1. Although, with decay functions, we often see it notated a different way, where we still choose a b value that's greater than 1, but we make the exponent negative. Why does this qualify as a decay function? If I look at this example where I have 2 to the negative x, having a base of 2 is greater than 1, so we would think that the value would be growing over and over again. But remind me, what does a negative exponent do? It switches it to the denominator. And then I can rewrite this just using my exponent rules as 1 over 2 raised to the x. Now, all of a sudden, I have a base that is less than 1. It's in between 0 and 1, making it a decay function. So we're actually going to see decay functions written like this a lot, where my base is still greater than 1, but the exponent's negative, and that makes a decay function. But regardless of what type of exponential function I'm working with, exponential functions have certain properties. First of all, what's the domain? The domain is all real numbers. I can plug in any x value I want, and it'll give me a valid output. But my range is strictly positive numbers. When you plug a value into an exponential function, your output will be positive as long as I haven't multiplied, as long as I don't have a negative coefficient or a negative starting value. The y-intercept for a basic exponential function is 1. That, of course, will change if you have a coefficient or if you have a different starting value. But for any just basic exponential function, your y-intercept is 1. Well, what else do we notice about these two functions? Both of them have a horizontal asymptote. They both approach 0, but will never actually reach 0. And that makes sense because take a decay function. If I'm always multiplying by a fraction, if I'm always multiplying by 1/2, you're always getting halfway closer to that 0, but you'll never actually make it all the way to it. And so both of these functions will never actually reach 0. So with that in mind, let's think about maximums and minimums. Does this function have any maximums or minimums? No, it doesn't. It doesn't have an absolute max or an absolute minimum because it never reaches 0 and it goes up to infinity. It also doesn't have any local maxes, which means, does this function have any critical points? It doesn't. The growth function is always increasing. It never switches from increasing to decreasing. The decay function is always decreasing. There are no critical points where it's going to switch. What about concavity? Both functions are concave up. They both have upwards curvature. So what does that mean about inflection points? There are no inflection points. And this is true for all exponential functions, all basic exponential functions. Okay, but speaking of critical points and concavity, let's talk about derivatives. Hopefully up to this point, a lot of this was maybe a review. If you've already learned about exponential functions, then a lot of this is going to sound pretty similar. But let's now relate this to derivatives. Well, another important property that all exponential functions have is that the rate of change of exponential functions is proportional to the function value. What does that mean? Well, remember, we now recognize rate of change as talking about the derivative. So what this means is that the derivative of an exponential function is equal to some constant multiple. You could use c, or you could also use k for the constant of proportion, times the actual function. And if you think about it, it makes sense because if we come back and look at the graph, the larger the y value, the higher up I get on my function, the faster I'm growing. And the lower I get on my function, the slower I'm growing, right? As I get close to 0, my slope is almost perfectly flat. It's flattening out. But as you get higher and higher and higher, that graph starts growing steeper and steeper and steeper. It starts growing faster. And we'll relate this to specific applications. Once again, we'll relate this in 3.3 and 3.4, where we'll talk about how it makes sense in specific contexts. But this is one very important property of exponential functions. And so with that property, what does that mean? That means that if I want to take the derivative of some exponential function, then what I should end up getting is just that same exact function multiplied by a constant, which makes for a relatively simple derivative. If you take the derivative, you get the same exact function just multiplied by a constant. The problem is, what is that constant? So as mathematicians started to struggle with this, they asked themselves a question. For what base value, or b, will this constant end up just equaling 1? because that would make for a really simple derivative, where if you take the derivative of it, you end up with itself, because 1 times b to the x is just b to the x. So what function, or what choice of b will end up doing that for me? Well, it turns out with a little bit of work, mathematicians were able to discover that this works for a number known as Euler's number. Some of you guys have heard of this number, but it's an irrational number, meaning it's a non-repeating decimal that goes on forever. Non-repeating, non-terminating. And it's right there in between 2 or 3. And what's cool is you can actually see this if you play around with this on Desmos, like on a graphing calculator. You can graph 2 to the x, graph 3 to the x, and zoom in right there at the y-intercept. And if you zoom in close enough, you'll see what their slopes are, right? Their instantaneous rates of change. And 2 to the x has a instantaneous rate of change that's less than 1, and 3 to the x has an instantaneous rate of change that's greater than 1. And so sure enough, if we pick Euler's number, which is between those two, we get an instantaneous rate of change of 1 at the y-intercept, which shows that this constant value is equal to 1. So what does this tell me? What was all of this conversation talking about? If I take the derivative of this special exponential function e to the x, e is no longer an unknown value, e is a very specific number, then I just get the exact same function, e to the x. Makes for a really simple derivative. The derivative of e to the x is just itself. You keep it the exact same. Notice how that's very different than a power function, because these are two very different types of functions. Well, now that we know that, what happens if we throw a constant up there with the exponent of x? This is something you'll see quite a bit. This is a very common type of function, and we'll learn about why in section 3.3 and 3.4. Once again, that's where we'll get into really cool contexts where exponential functions work really well to model certain situations. And so this is another type of equation that you'll see quite a bit. E to the kx, where k is some constant. Well, what's nice is now that we know how to find the derivative of just e to the x, I can use chain rule to find this derivative. So if I treat kx as my inside function, then I can use chain rule to find this derivative. What's the derivative of e to a value? We just learned that. You end up with the exact same thing. And if I use chain rule, what do I do with that inside function? I keep it the same. So I get e to the kx, but now I need to multiply by the derivative of the inside function. If k is just a constant, what's the derivative of kx? It's just k. So another relatively simple derivative formula, if I have e raised to a constant times x. And you'll see plenty of examples like this on your homework. But that takes care of 3.1. This section, we're only going to focus on base e because that gives me the simplest derivative formulas. We'll eventually get to how do you take a derivative if the base isn't e, but we won't get to that until 3.5 and 3.6. So for now, this is all you have to worry about. Those are my derivative formulas for an exponential function with base e. So go ahead and start on the homework, try a few problems, and then as you get stuck, check out my examples video. Good luck.